Okay, we have this really interesting formula on the board that combines Laplace transforms and integrals. And it's kind of amazing what we have here to think if we've got a product of functions like this, if we have one that can be expressed as a Laplace transform, we can basically just shift the Laplace transform from the f function to the g function like this. Now, I was trying to do a video on this a couple months back, but I don't really remember where it ended up. I might have just deleted the video. Because the thing you'll notice about this, even though it's a great formula, it's a little tricky to find good examples. Because when you start messing with this, what you'll find is a lot of things that are nice Laplace transforms here. Because the integral is going from 0 to infinity, a lot of the integrals are going to diverge. And then the other thing is how you choose your f and g. A lot of things don't have nice Laplace transforms or nice inverse Laplace transforms. So it's hard to find good examples. So anyway, to get started with, let's just derive the formula. I'm going to start with the left side, this first equation over here on the left. And what I can do is we can take the definition of the Laplace transform on this. And the one thing you'll notice is I've reversed the variables. You have to be kind of careful with the variables here. I mean, in a way you don't, because it's all definite integrals, so the variables don't matter and you can switch them out, so you can switch them around however you want. But just to be consistent, like if this integral is going to be with respect to x, we need the Laplace transform to output an x here. So that's why I've reversed where the input here is s and this is x. So I'm going to be doing that throughout in order that we get the right variables to pop out. So to write this by the definition, still an integral from 0 to infinity. Now for the e part, we reverse the variables. So I'm going to write it as e minus xs. We'll have this f of s function ds. And then for the outer integral, we're integrating with respect to x. And then from here, let's just multiply the g of x in. Even though it's a constant with respect to x, I can multiply it in. And then from here, let's just swap the order of integration on this. How do we know we can do it? Well, we really don't. Like I said before, a lot of these integrals are going to diverge. So in order to do this, we'll make the assumption that we've got something that's going to be nice, it's going to converge, and then we're okay to do this. So now that I've swapped this f of s function, now this thing is a constant with respect to x. So we can take this out front here. On this e minus xs, I'm going to actually swap the variables just to make it look the way I want it to right there. So we'll swap that back. And so that's what we have. But then this right here, now this is a Laplace transform, but it's back in the form we're used to seeing it, where like our input's g of x. So this is going to be the Laplace of g of x, where now we're going to be outputting an s on it. So let's write it this way. We're going to have, again, integral from 0 to infinity, f of s of this Laplace transform. And then here you'll notice what we have. This is really the same thing as this. We can just, it's a definite integral, so we can just swap the variables back. That's the only difference here. So what I can do is, just for this formula, put everything back to x. Not that it matters, of course you could leave it, but let's put it back just to make it look nice, and we'll have it all be in x. And so this is going to give us our formula equating this thing that we started with to this right here. But now one more thing I want to look at before we finish up. There is like a different form of this integral Laplace situation. I kind of like this one because it's so easy to remember that you're just swapping the position of the f and g. So that has an advantage to it. But this other formula's got kind of another advantage to it, even though it's like a little more complicated, I think. So let's take a look at that right now. Okay, so for this other formula, and this might even be more common. I've actually seen it quite a few times written this way. For this, we'll substitute in for our function inverse Laplace of another function h of s. By doing this, we're not changing anything. We can still have it output an x if you want. If you want to think about like what this could be, if you had something like, let's say the h of s was 1 over s squared plus 1. Well, then the inverse Laplace is going to be what Laplace gives you this. And that would just be sine, where we're using the variable x. This is just sine of x. And so nothing wrong with this being our g of x function. If you wanted to figure it out the other way, you could just take the Laplace transform of sine x to get to 1 over s squared plus 1. Again, you can kind of see the potential problems. If I chose something really complicated for h of s, then I can't take the inverse of it. So that kind of thing. But if we have something nice, we can get back our g of x. So we'll do this substitution here. So then rewriting this left side here, we've got this integral, we've got the Laplace transform of this thing, and then we'll just plug in this thing right here. But then on the right side of the equation, what's going to happen, now we have our f of x, but now this thing, we throw the inverse inside the Laplace transform, we just get back this. So we just get back to h of s, but now I'm going to swap the variables to make this all work. So we'll call this h of x dx. And if you don't like using h, we can just flip that back too, because that's just a label. So if we want to use g, we can use g right here. But now here we've got our different version of the same formula. It's really the same thing, but it's kind of nice this way in a way, because now we don't have to worry about starting with a Laplace transform. We're just starting with two functions. Now the transformation might be a little more complicated, because for each of these, notice that for the f function, we need to be able to get the Laplace transform. And for the g function, we need to be able to take the inverse. And we still need all this stuff to converge. So it's really nice, but off the top of my head, I think I only know like 2 examples that I know how to do, or I know for sure work. This is on the Wikipedia page. They just did sine x over x dx. We know from, I've done like 10 videos on it, and it's pi over 2. But how do we do it with this formula? Well, let me think. If we break it up, instead of writing it that way, let's write it like sine x times 1 over x. And maybe I will use this second formula here, putting it in this form. So like for the f piece, we want to be able to take a Laplace transform. Well, it's easy to take the Laplace transform on sine. And for our g of x, we want to be able to take an inverse. Well, this thing is going to be easy to inverse right here. So if I do this, what's going to happen? Just using this. So like first for our Laplace transform of sine x, that's what we saw before. That's going to be 1 over s squared plus 1. Yeah, we'll leave it. We'll deal with s right here. So I'll write it as 1 over s squared plus 1. And then here, taking the Laplace inverse of 1 over s, that's just going to be a 1, right? Because the Laplace of 1 is just 1 over s. So we just get a 1 there. See, it's a very simple example. But then we can just go ahead and integrate this. And of course, see, it's confusing with the variables. I mean, I know I've done it a bunch of times myself because I'm so used to using s, but we need to integrate with respect to s here. We do that. We get just arctan of s evaluated from 0 to infinity. This part's nothing. Upper bound is just pi over 2, and that's our solution. Okay, so there you go. Great formula with the Laplace transform. I'm going to have to look up for some good examples to use on this. Everything I've done almost, other than like this simple stuff, is diverged or been impossible. So I'll keep an eye out. Thanks so much for watching. Have a good day.